here the Fresnel stars, which are the stars here, and here correspond to, I would say, carbon-enhanced metal spore stars on the main sequence, which are the black areas, and evolved carbon-enhanced metal spore stars, which are the red point here, the red areas here. I have indicated two kind of models. The first one, the blue line, corresponds to what happens when we take the 60 solar mass stars, beginning its evolution with 800 km per second, removing all what is about a mass cut of 30 km or 30 solar masses, so the rest will be swallowed by the black hole, and diluting with 100 times more interstellar medium material. And this will give this curve here, okay, the observation, and again. If we take exactly the same model, but non-rotating, I have the dotted curve here. It will be okay for carbon and oxygen. Unfortunately, this model did not account for the networks allowing to make prediction for this heavier element. So I have only CNO elements here. But already from the CNO element, you can see that without this mixing between the core and the right-bending shell, you will never have enough nitrogen to explain the carbon, at least those observations of carbon-enhanced metal spore stars. The red curve is from the envelope of intermediate mass stars. But before the AGB, it's really at the time when the star has finished more or less its helium burning phase, and it's at early AGB phase. It's just, of course, it would imply some strong mass loss at that stage, or some binary transfer at that stage. But anyway, you have the curve, dashed line here, which relatively well fit, by the way, here for the sodium, magnesium, aluminium. And again, you have the non-rotating case in red here. What is interesting in these models is that depending on the dilution between this material and the interstellar medium, you can have helium-rich stars produced. If you have a small dilution, at least the massive stars will produce very helium-rich stars. Because this material, corresponding to the blue curve, is also helium-rich. But of course, if you dilute with a lot of interstellar medium, like it is the case here, of course, this helium will be diluted and you will not obtain a lot of helium. But helium will be a kind of measure of the dilution in some way, in this kind of models. Also, lithium can be used as a dilution because in the massive stars, lithium is destroyed, completely destroyed. And if you dilute with a lot of interstellar medium can have some lithium, of course, remaining from cosmology and from some destruction by stars, but still it has some level of abundances. You can see also that this, for the massive stars, this kind of feature here between carbon, nitrogen, oxygen depends a lot on mass cut. If you decrease the mass cut, you go deeper and deeper inside the massive stars, you will have a feature which goes, which will produce a V like this one, but just shifted at higher value. Okay, I think that I have spoken during 55 minutes. I don't know if I stop here.
Yes.
Okay. So I had still some things to say, that I will skip this point. And all the story about the... Okay. I have maybe just, as a conclusion, two slides to show. This is a kind of analogy in that sense. The analogy is that when we look at these very metal spore stars, we are a little in the position of looking at a meal prepared by a cook. And this cook, of course, we want to know who he was. And the carbon-enhanced metal spore stars are the meals, and the cooks are stars of some types. So what I showed you is that at least for some of these carbon-enhanced metal spore stars, the cook can be very big, it can be massive stars. And the second point, probably it was rotating on itself very fast. So dancing very fast. This is my first conclusion. The second point is that it's funny to think about rotation. Rotation, in some way, is a little like metallicity. Metallicity is a small amount. In the Sun, it's about 1.4% of the total mass of the star. Rotation is a small effect from the point of view of energy. It's maybe 1% of the gravitational energy of the star. But both metallicity and rotation makes a huge difference in the way the stars are evolving. There are details which have impact. And I would like to share with you this sentence by Leonardo da Vinci. The details are making the perfection, and the perfection, of course, is not a detail. So, thank you for your attention.
Thank you. Other questions?
I have a couple of questions. In the last biography, you have shown with the abundances of the models compared to the. That's one, okay. The case of the seven solar masses models, the enhancement of CNO is due to the mixing induced by rotation during the Coriolis environment. It has nothing to do with the dredge up. Okay. So that's the first. The second question. Questions concern the difference between advection and diffusion. I completely agree that meridian circulations is an advective process and should be treated with an advection equations and not with the diffusion one. By the way, I noted that you use the advection equations only for the transformal angular momentum, but not for the mixing induced by. This is because in practice is the same, not in principle, but in practice is the same, or there are some physical reasons to do that.
This is a very good point. Actually, the physics should be the same. And as you said, we could compute the mixing of the chemical elements, also accounting for an advective and a diffusive term. Now it has been shown by Sam and Chavoyer that for the case of the chemical species, you can apply the pure diffusion equation. Why it is? It is because one of the key a priori assumptions in the theory of Jean-Paul is that in a rotating star you have a strong horizontal turbulence, very strong, which is called the DH. In some way, it can be understood due to the fact that any gradient of omega along an isobar will be rapidly washed up by instabilities, shear instabilities, because the shear instability has not to struggle against gravity, because it's an equipotential, more or less. So, you will have what you call a cellular rotation rate and a strong horizontal turbulence. Now, for the chemical species, let us make the thinking experiment. You have some column which is going up due to advection along the polar axis, and the column which is going outside along the equator. For the chemical species, due to this strong horizontal turbulence, you will mix everywhere, and it will make no difference. For the angular momentum, it's not a quantity which is, I would say, of a similar nature as the chemical species, in the sense that for the angular momentum depends on the distance to the axe of rotation. If you move along the polar axis, you transport no angular momentum. Along the equator, you transport angular momentum too. And it's why, it is a fundamental, I cannot explain,
yes, I
but it is why you cannot make.
It's okay.
I have a question. You are considering, I imagine here, a very low metallicity, so you are assuming this kind of rotation velocity, which is very high. But
not the angular momentum.
No, of course, I agree with you. My question is, according to the current observation, if you consider objects with mass of the order of 2 or 3, 2.5, with a solar metallicity, I'm referring to the work by Bomser and co-workers, you have the evidence that the mean rotation period of the core is very observation used mixing. So if you apply the same scenario to low metallicity, if you assume that this is exactly the same also to low metallicity, in this case you don't have, I suppose, mixing, because you are...
You know, I am not sure about that. First of all, I think that your point is very interesting, I must say. And this observation by through asteroseismology that the core of red giant present a contrast between the rotation of the core and the rotation of the envelope seems to be much lower than what is predicted by this kind of model. This is the point. But still there is a strong gradient of omega, which may be sufficient to trigger mixing. I am not sure that it will completely cancel any mixing of this type. But this, of course, has to be checked. I don't know. The second point is that, of course, this observation was related to low mass star. We are speaking about high mass star. We don't know if it's the same.
Yeah, of course.
But we are at the time making a trial, in the sense that we are first trying to extract from this observation of the red giant the diffusion coefficient which is needed to transport the angular momentum in a way that we reproduce this observation. And then we shall apply to massive stars, and we shall see exactly what you want to look, whether we have still sufficient mixing, especially at low metallicity. I think this is the way to go if you want.
Yeah, of course, but if I remember, there was a work by Marquez et al. 2013, which fixed, let me say, lower limit, at least for a 1.5 solar massive, and you need a factor of 100. You have to increase the transport of angular momentum by a factor of 100 in order to reproduce observation, at least for the subgiant. I think that for the red giant case, if you consider also clamp stars or iridium-bearing stars, you need a much higher value.
Maybe it's right.
But sorry, just another comment. I agree with you that mixing depends on the profile, so on the gradient, but it depends also on the value of the omega, on the local value. So if you decrease the level, you have also a gradient, but the maximum level of the rotational angular velocity is lower.
The shear depends only on the gradient. It's you depend on the omega, but the shear depends only on the gradient.
Okay.
Yes. But you, as you know, by the way, you see, it's funny because sometimes when you slow down the star, you can increase the mixing.
Yeah, of course.
Because you steepen the gradient. We did this by accounting for some magnetic braking at the surface of stars.
Yeah.
Recently, we also looked at post-binary evolution. And in post-binary evolution, you have a synchronization part where the secondary can spin up or spin down the primary in order for the orbital period to be equal to the rotational period. And in both cases, spin up or spin down, you produce a gradient at the surface which produces a strong enhancement of the mixing. So the mixing of the chemical element is due mainly to the gradient of omega, not so much on omega itself.
Okay. By the way, these observations for the moment are biased in mass and metallicity, are very concentrated in mass and metallicity. So
yes, of course.
I think
This is but still, as always in astronomy,
very interesting. But
it can be interesting to look just like to look. If we want to observe this, we want to reproduce this, what we have to do, and we apply the same rule for other metallicity, other mass, of course.
So, okay. Yes. Question? Okay. We can close here. We thank George again for the